Thank you, Mónica. Hola, ¿cómo están? ¿Cómo han estado? Okay, so how have you felt about this case so far? Because we're going to be continuing predicting housing prices. So let's see. Let's ask this. Give me some reaction here. Sí puedo hablar español, solo no muchas palabras técnicas no las conozco. おはようございます。Buenos días a todos ustedes. Caribbean. Soy salvadoreña, no soy caribiana. Okay, so let me share my screen here so that we can continue with our case. Give me 1 second. So we're gonna continue with our Milwaukee housing pricing prediction. I dropped in a little bit earlier so to see how you were doing the first portion of it. I know it's hard to follow Danica because she's a wonderful instructor. I worked with her for the last couple of empowering programs, and I know she's a great instructor as well. So, but it's also funny that she mentioned that there's some houses that with no bathrooms. So, because I lived in one of those houses, well, they had a toilet, but not a bath, like or not a shower. And that's when we moved to Japan. So traditional houses in Japan didn't have baths in the houses. So there were a lot of public houses historically. Furo, yeah. And so when we moved there, we were moving from El Salvador, and we rented this really cheap apartment, or my family did. And it was a very old apartment, so it actually hadn't updated. And it only had a toilet and not a bath. So we will just walk down the street and pay to use the public bath house. So that was, I was a kid, so it was kind of fun. And I'm not sure how my parents felt about it, but for me, it was like fun 3 months that we experienced that. To my first introduction to living in Japan it was kind of fun. And anyway, so that's a side story. So let's get to our case. So we are going to continue here. I know you have done a little bit of already quite a bit of introduction to linear regression, and we're going to continue with that, of course, and we're going to see if we could improve the models that you've been working on so far in the first portion of this case. And again, the business context is the same. We're still wanting to predict these housing prices, but we want to have a better model, essentially. So our job is to improve these to predict these prices. Okay? And we are going to be learning how these categorical features are actually variables are being used in the regressional models, and then how to see how the model is doing, how to improve it, and then look at multi-collinearity. Okay. So this is the same as before. So, well, we are importing our packages, of course, but we need to, again, clean up. It's because the same data set, we need to clean it up. And then we're going to drop all sell prices that are below 2,000. That may not be real, but like, because of the analysis that you've done so far, like, we think that they are not actual real numbers. Okay. So this part is exactly the same as you have done. So I hope this is just a review here. So the same, we're importing the data and changing this to categorical data type, and then removing the unused categories. Okay, so that part is exactly the same. And now we are also introducing this. So anything that it's built before 1800, that's really old house, we're not gonna consider. But and then the square foot has to be a positive number, lot size the same. Property type is also just residential. We're not taking into account any commercial. And of course, the sell price is the one that we just talked about, has to be over $2,000. All right. And this is how our data looks like now. So the only difference compared to before should be that the sell price, there shouldn't be anything below $2,000. Okay. Let me move this real quick. Training versus testing this. So we generally, when we train a model, we don't use all the data that we have available. We want to split our data set between training and a test set. And the test set is used to evaluate our model, essentially. And we do this because you could have a great model, but you may be actually building a model that is extremely specific to the data that you have now. So once you introduce new data, it may not be behaving the way it should be, or the way you were hoping to do, right? When you're building a model, the hope is to predict something that you haven't seen. So in order to combat that, you split the set, you train it with that subset of the training set, and then you bring in the test set to validate your model. Does that make any sense? And this, yes, overfitting is a term, like, it's very common when you make something very specific to a data set that you're training with. So if you say, for example, we split this test and training set, right? You train it on this training set, and you find that it does extremely badly in predicting using the test set. Now you know that you made an overfitted model, because it's doing really good when you're doing the training set, but it's doing not well. It's just like not a good model overall. I mean, it's a good model for like that small subset of the data, right? Okay, sorry, I'm scrolling too fast. So to do that, we have to split our data set, like I said. So let's take a moment to see if you could do this on your own, and then we'll work on it together. So let's take a few minutes to do it. I'll give you some time to split it. So the instruction is to split it 80% training set and then 20% training set. So anywhere between 7 to 80 is pretty common as a training set. So this is a good starting point. And then you're going to be fitting your linear regression model, just like as before you did earlier in the earlier case, with the log of sell price and the response variable being district units and the log of the square feet as predictors. Okay, so and in order for all of us to have the same set, go ahead and use this MP random seed and this number, big number, so that we all have the same result at the end. Okay, so let's take a few moments. Maybe I could play some music in the meantime.
Si los reptiles cantaran bajo tu ventana coplas de su propia inspiración, entonces ¿dónde quedo yo? Si los árboles lloraran, si se pudieran mover, si la lluvia reprochara el momento de caer, si el desierto hiciera versos
Oh, sorry. I did not realize I was muted. I was trying to answer your questions. And so validation and test sets are generally used interchangeably, so they're equivalent. Training set is the actual data that you use to train your model, okay? And we'll take a look at it here, how you use the different sets, but the test set is what you're using, test or validation set is what you're using to assess your model, to see if your model is good. Train test split is an sklearn. We don't have sklearn here, but you could do it without it also. Some of you already finished. The seed number can be any number. We just chose this one here. And sorry if the music was really loud. I don't actually have a good sense of how much you hear on your set. All right, so how many of you have finished splitting your, so let's ask this, have I finished? Okay, so there's at least 10 of you here, so we're gonna go ahead and look at this. So again, we're just using this random seed so that we all get the same number at the end, like the same split, because we are randomly splitting. If you don't use this random seed, all of you are gonna have a different split. Okay. Yeah, the sklearn, the scikit-learn package is really awesome too, but again, it's worth knowing how to do it also manually. All right, so in order to be able to split, like we need to know how much of the data we have, right? So this is just getting the number of rows essentially, and random choice so that you could multiply it by just picking like essentially 0.8, so 80% of your data. Okay, and then so you pick it and then you're not replacing it, so you don't pick the same data point over and over again. And this is one example, by the way. There's definitely other ways to do it, but I'm just showing you this way. And then you're also getting the index for the test set. That is the set that is not included in the train set. Okay, so now we could get, now that we have the index, we could get our train and test. And you should be able to get, so the number of columns, 19, should be the same between the train and test, but the number of rows will be different. This is like 80% of the data, and this is 20% of the data. Scroll up or down? Not sure which way you want me to scroll. anyway, so I'll share. If you get different numbers here, it shouldn't be the end of the world for our purpose, but if you want to see exactly the same code, of course, I'll share my code here. Let's see, so that you could see it. Okay. All right. So does this make sense? So we have the 80% for our training set and 20% of our test set. And let's take 1 minute to see if you could fit your model using the training set, not the train set, not the test set. Okay. And start giving me an emoji if you finish. So let me see. Yeah, I know you're going to have all the answers posted on the polls and answers. So I'm not necessarily going to post everything. So I just gave you this so that you could just follow along quickly. All right, quite a few of you are done fitting your model using a training set. Again, we're trying to, so the predicting variable, so or the variable that you're trying to predict is the sell price. And in this case, we're actually using the log. And then the response variables are district, units, and the log of the square feet. Okay. All right. So this is exactly what we have here. So we're feeding it to the OLS model. And you're probably not familiar with it. This is essentially the formula. So the log of the sell price, and you want to predict it using the district, units, and log of the square feet. And the data is your train. Remember, like we use this, define this train and fit it. Notice that we only using the train set. And now we could look at our model. Okay. So can somebody, or does somebody want to summarize a little bit, like the overall result of this? I know you've dealt with the AIC before, and hopefully the R squares, I'm assuming. A lot of you are typing, but I want to see what you all think. Just give me one thing. You don't have to like give me the whole summary, just like a little bit. Yeah, 60% of the variability. So that's from the R square. That's awesome. The MP random seed and pandas has also some random state. I think random state is specific to one thing that you're doing, whereas random seed, it's more global, I believe. Residuals are not normally distributed. Okay, is that from your previous case, or you have them more here? T12. Okay, the district. Yeah. Almost all values are significant. Yeah. Yeah, except for this district. All right, these are all good answers. So anybody else wants to share? Okay. Kurtosis is greater than 3. Yeah. Awesome. All right, so let's move on to looking how we could see how the categorical features are actually handled in these models, okay? And then you notice, okay, here's a lot of different district, right? Because this is a categorical feature. And it is handled essentially, depending on what the value is, it's going to be handled differently. That's because under the hood, it is essentially what is handled as one hot encoding. So it says here, one hot encoding. So it's creating values by, so we have it here and say we want to flip the categories. So instead of having it here, we flip it so that the categories are to the right. And now we mark them as one with 1 and 0, whether that's true or not. So if it's true for category B, you say yes, otherwise it's 0. Okay? And because these are districts, it's always going to be just one true along the way, right? And that's true for any categorical values. It's essentially going to be only true for one of the categories. And these are called, essentially, you're dummyifying. That's really the wording that you use, like you dummyify your data. And so that like computationally it could be handled. Okay, does this make sense? So you're just flipping. So let me see if I could draw here. So if you were to take this and flipped and say A, B, C, right? So for example, here, let's say it's me, Amiko. It's really hard to draw with this. Let's say I'm gonna say Anna and Tanika. And for example, what type of car do we have? I have a Subaru Impreza, so I say SI. Anna, I actually don't know what she has, so I'm just gonna guess. Maybe she has a G-Wagon, right? So G, oh well, Mercedes G, so MG. And then Tanika has a Honda Accord, so HA, right? So in this case, if we dumbify it, we're gonna have the same rows, but instead, it's say Subaru Impreza, Amico is 1, Anna 0, Tanika 0. G-Wagon, so Mercedes G, 0, 1, 0. And then Honda Accord, 0, 0, 1. Does that make sense? Oh, Anna's car, electric vehicle. There you go. Yeah, so this makes sense. All right, so let's clear this. Awesome. Let me get my cursor back. So the easiest way to do this is using this PD, so pandas get dummies, and you don't have to do it manually like we did earlier, but so you just so you have your data frame, and then you choose the categories, of course, and then you dumbify those categories. And you drop the first category. Why do you think that is? I guess I shouldn't have erased the first one that I just drew right now. Let me see if I could bring it back. Redundancy, yeah. It's also logically, let's think about it for a second. Right, so if we bring, sorry, there you go. Yeah, can I grow? So the car example, right? So we have Amico, Anna, Tanika. And then we had Subaru Impreza, oops. Mercedes G-Wagon, and then Honda Accord. Right? So it's 1, 0, 0, 0, 1, 0, 0, 0, 1. If we remove these, first one, how would I know what I have? For example. Yeah, these are all really good answers. But also logically, we could kind of infer if we know that there's 3 categories. And if it was 0, 0, then Emiko must have Subaru Impreza, right? So as long as we keep all the categories as register, yeah, awesome. So you already know this. And essentially, the linear models from StatsModel, that's what they do. They handle the categorical and they just drop the first one, and they're using as a reference. And it will automatically do that. So I hope that answers your questions, Victor. If 2 of 3 columns have 0, yeah. Yeah, we pretty much drop it every time. I'm not sure if there's a maximum, but I think with experience you'll know. There's different ways of handling it, but that's kind of outside of the scope of today. So let's stick to here for right now. So in this case, we have these ABC categories, and we drop the A category, and then we have 2 columns, right? So we know 4 here, we know that it's going to be category A. That's the reference category. Okay. So let's read here for a second. The choice baseline changes the coefficients and their interpretations. You know that, right? But the coefficient, or for example, for district 3, should be in relation to district 1 whenever you interpret the model, right? So that's your baseline. And it really doesn't matter what the baseline is, because like you always know what the baseline is. It's like you know the one that is dropped is your baseline. So do you understand, Luis? Is it Luis Alberto? I'm not sure, but like if you go by 2 names. But if you drop it, you could still figure out the category for 4, for example. That's going to be your reference, and you diminish redundancy. Why do C and A are written after? You mean like this underscore B? That's just the name of the category. So it's just saying for category B, that this is the entries. I'm not sure if I'm understanding your question. Yeah, there you go. So Julio just posted a good way to visualize it. So you do this, but if you drop the first column, or sorry, in this case, the second column, category A, you still get the same results as if you had 3 categorical columns. Oh, sorry, 3 of the underscore category columns. And when most softwares or programming models drop it, most often is the first occurrence in the alphabet. So the stats model is not an exception. It's definitely going to be whatever the first letter in the alphabet category, the name of the category is. So in this case, for category ABC, it's always going to be category A. The intersect will be the effect of that category. The intersect, I'm not sure what you mean, but what intersect? Intersect between, or just the intersect of the model? The intersect will be the, oh, I see what you're saying. I think I know what you're saying. So yes, the intersect will be the yes, you're right, like the category of the baseline. So your baseline category. All right. So hope you're doing okay so far. So now from this last model where we had, what did we have? District, square feet, and number of units in the house. Sorry. Sorry for scrolling. We are going to also add style. And you could do this in many ways, of course. Style is also a categorical feature. So you have to do that. You could either just let the model take it, or you could use get dummies to make them dummy variables before you input them in the model. So let's try doing that. We'll actually make them before we feed them into the model. And you have some hints because there's a little bit of weird things that may happen if you don't use this quote notation using the Patsy. Patsy. So let's take a few minutes here.
I'm waiting on a warm and sunny seashore, yearning for the one that I adore. My heart is true, I'm thinking of you forever. I'll love you, kind of. I see a sunbeam dancing on the water, surfing on
So
a
this
wave
song is
that
called
comes
Kainoa.
to shore. The
For
promise in
a
that
Hawaiian
beam is a long
artist
awaited
that is
dream. It
long
tells
past
me
now,
that you
gone now,
love
but
me, kind
is like IAG was his like, because nobody could pronounce his full name. Israel.
Now day is done, the
I'm gonna
sunset's
butcher it, I know.
kind
Makawiwo Oli, I think.
Stars are
The long last name.
peekabooing from above. The moon gets brighter still. In my heart I feel a thrill.
So the Patsy quote, it's so that here, if you just do it the way you think you're going to do without using it, you're gonna end up with quotes inside and then outside, and that's gonna mess up your formula.
Palmy shadows on the sand. They dance beneath the moon while the breezes hum a
Play that one,
tune.
Andrea.
They do this 'cause they love you, kind of, kind of. I love you. Do-do-do-do. You. Do-do-do-do-do.
Okay, how are we doing? Were you able to make the new model using the get dummies? Okay, so as reference, remember before we had this. This give you hints a little bit of how to get the style damified. So Carlos, you're on the right direction. It looks like you're still working on it. So let's give it a couple more minutes. See if I could find you wanted to hear Somewhere Over the Rainbow.
Ooh, somewhere over the rainbow,
Awesome.
way up
Yeah, Maria.
high, and the dreams that you dream of once in a lullaby. Oh, somewhere over the rainbow, bluebirds fly.
Let's see how many of you have finished.
The dreams that you dream of, dreams really
Hope,
do come true. Ooh, someday wish upon a star, wake up where the clouds are far
let's see if we can move on. I know you're enjoying this combat. I'm gonna cut it a little short.
behind.
All right, so first, I know, Carlos, you were on the right track, but we actually need to pick only the unique ones, right? So Maria got that right, like so, and then you damify it. And in order to keep it consistent with what the base, without doing anything how stats model is gonna handle, we'll just sort it and we'll drop the first to be able to drop the first baseline category. Okay. So we'll damify it and then we'll drop the first one. You see how we don't start from 0, but we start from 1. And we'll add it to our formula. Okay. Hope that part makes sense. So you have your formula starting from the sales price, and then you add all the styles that you damified, and plus district units and the log of the square feet. Let's see. The prefix arm in the argument. Oh, so when you create dummies, right, you have to be able to distinguish what it is. So how do you want to add it together, essentially? So it will be like here, in this case, category underscore something, right? But here we're telling it to not add anything. And then the separator, it's also not. It's just gonna purely add the different styles straight as category or style, sorry. It'll be style, whatever the style is. You'll see here in a second. So, and then we feed that to, again, to our train model, or sorry, a train set. And as you can see here, you could see we're just having this. So there's no prefix or any kind. We'll just straight out using the name of the category or the type of the category for the model. Okay, so we have this model. And then when we compare it to the model that we've done before, like no dummyifying. And let's see here. Let's keep it here. So by level, it's 0.1548. Let's see if I could find it. By level, 0.1548. I'm kind of giving you an answer to the next question, but as you can see here, it really doesn't matter how you do it. Obviously, it's easier to not have to dummify this, right? It's obviously, there's a lot more code here compared to how it's handled here. However, now you understand how stats model is handling your categorical variables. You know how it treats it and then fits it into the model. Okay. So I hope that helps. And then let's look at which one of these is the best style if you were buying a house, or maybe I should say selling a house, because like you don't actually want a more expensive house, mansion and Tudor. So is that the one here? So Tudor is 0.3636. Ranch is 0.3. Yeah, mansion here 0.36. Right. So these are, they kind of make sense, right? That they're going to be more expensive. So the mansion style. I mean, I'll agree with Hyman. Like I will also add Tudor to it. Tudor always makes me think of Sing Sing in England, but I obviously don't know enough about types of styles of houses. I'm not sure if that's what it means, but we'll go with that. But the mansions, Tudor, castles, whatever you call it, those huge houses are going to be obviously more expensive. So that makes sense. So it kind of gives you, sometimes when you're looking at it, when you model, it's good to check also that it's behaving the way it makes the most logical sense, right? Because it's also, it's not really how you define a model, but it's a good checkpoint. Okay, so that's a Tudor style home. Not, yeah, okay. There you go. Here, somebody asked before, why do we remove it? What for, right? So what if we didn't remove it? What if we use all the styles? So here, remember, we started from 1. Here, we're actually using all of them. So what happens to that? So, okay, let me ask you this question. Do you think this is a correct model? Yes or no? And let's see if you could give me some of the reasons why. why or why not, I guess. Do you think most of you think it's not a correct model? Why is that? Remember, we are not removing this here. We are keeping it. Yeah, multicollinearity, yes. Overfitting, no, really. It's more redundancy. Okay, so let's look at here. So we are fitting the model with all the categories from style, and let's compare it with the other model where we remove the baseline. Okay, so when we do that, you could do this by, we just made a new data frame, getting the coefficients. Okay, and so what do you think? Oh wait, we need to look at here. You need a baseline to interpret. That's yeah, so right, so these are all good points that you're raising here. But as you can see here, the style 1, so the like AP, so this is like AP1. Let's see, where is that? There you go. So when we subtract this, we get this difference. And when you subtract the coefficients from the first model to the second, you could see that this is a very small value. And so from this, you know that the models are pretty much the same, but as you mentioned, incorporating the baseline here adds redundancy. So we know that the values of all style dummy variables, except for the AP1, we'll know that the value of the dummy variable corresponds to AP1 here. Okay, this redundancies often creates numerical problems. So like I said, it's not wrong per se. It just more, the issue becomes that you're introducing multiple things of the same thing. So this is an example, and somebody mentioned this before. It's an example of multicollinearity. And we'll discuss this a little bit more in later in this case, okay? There are many combinations of coefficients that can be used to fit. Yeah, John, you're right. And then Catherine, essentially you always drop the first category. When you're dumbifying, again, this is the reason. You try to minimize redundancy. So you're pretty much always going to be removing that baseline category from going into the model so that you have a reference point. Okay, so when you're interpreting this, all this coefficient, if you remove it, it's always going to be in comparison to this style, AP1, the tutor is this much more expensive. Does that make sense? Okay. I hope the silence is not that you're confused. How are we doing? Let's see what all. Okay, does that mean that you're confused? The panicking emoji, I'm interpreting this. What is it that you're confused about? Let's see, I see people typing, so I'll give it a minute. Yeah, I know. Sorry about that. That warning, it's on both because you have actually a lot of features there that are adding to potential multicollinearity. Dropping the first one is made in order to have a reference. Yeah, Daniel, it's so that we order it so it's going to be the same result as the stats model. Can we repeat what we expect from the error data to look like? Oh, so you're talking about here or? Oh, wait, it's over here. So you mean this error also? So we are just comparing the numbers to these two numbers, okay? And they're extremely small here, so they're pretty much the same. That's really what it's saying here. They're very, 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 very small numbers. So when we're comparing the coefficients, you know that whether you have a baseline or without a baseline, your result is the same. Does that make sense? Okay. So without the baseline, so you're still, I mean, this is not a good nomenclature probably, because the result is still the same. You're still comparing it to this. It's more how we fed it into the model that it's different. Maria, we'll do this, so maybe that will address your question a little bit later. Yeah. There you go, Ronnie. Okay, so with the baseline, you could try, again, this is something that we're not gonna do this here, but you could do this on your own time. And remember, you could start adding or subtracting things, whether that improves your model or not. You get to decide based on, like, the AIC is a good metric to use for that, whether that's adding to your variable. But the danger of removing categories is that you're removing that completely out of the picture to be considered in the model. So in essence, you're removing the power to predict those particular categories, right? They're not even considered in there. So if somebody comes in and say, predict me the price of my triplex, it may not be the best for us to remove it in the original model, because we don't have any, like, reference point. We'll have to use the rest of the features to predict the price, and it may or may not be accurate. So yeah, there's some resources that folks are posting. So yes, repeat your, whatever you learn here, the more you do it, the more understanding you will have in every iteration that you do. Okay, so let's move on to metrics for evaluating your models. Okay. So, or this is more for residuals, so your errors. Recall that for any given data point, your old models, you're doing the difference between the model and your data point, right? And so you have a way to measure that difference or the error by using a few different metrics, one of which is the mean absolute error. And the mean absolute error is, we have it later, but I'll draw it here anyway, because it's sometimes helpful to have the formula at the same place here. So it's the sum of the So your predictions from your model, right? Minus the actual values. Or your true values. So, and you take the absolute of those differences and divide it by the number of your sample to have the mean, of course. So that's really what this formula is doing, right? In defining the MAE function. You're taking the mean, so this is this mean part, and then taking the absolute number of the difference. Similar, but so I mean these are a little bit of wording things, so I don't want to be, but it's yes, it's similar, Catherine. So, but does this make sense? So when you have a linear model and you have your data points here, right? You're trying to minimize these differences here, right? From here to here. And that's essentially what the old model is, ordinary least square. And there's like a metric that it's even essentially the same as what you're doing for the old model, where you're actually doing the same thing to measure these errors. So similar in the sense that you're trying to, it's not the accuracy, but like you're trying to have a measure of your error, right? So does that make sense, Catherine? So you're like looking at the errors here and having some sort of a measure for your errors. So what's the average of my errors? But because the errors is the difference, could be minus or negative, right? Depending on where it is. So this will be negative and this will be positive, for example, or vice versa. I did that wrong. That means that you have to correct that so that when you add it, you're not having this weird number. So in this case, in order to correct it, we did the absolute numbers. Okay, so let's see. And so now, all of this time, we're fitting the model using the train set, right? So remember, we use let's see here. Where's my model? We're fitting here using the train. Well, this is a train dummy. So I have to go all over here using the train set. There you go. Perfect. Thank you, Nati. And this the one that I think it's actually using the model that we fit a lot earlier, somewhere here. This log model. Okay, so it's using that and it's evaluating it here. Okay, so our model here, now we're entering the test, right? Because we want to evaluate it not using the train set, because that's going to be a really good number, right? Now we're evaluating using the test. I hope that clarifies some of the doubts that you had, some of like your questions about what's the difference between your train and test set. This is how you use it. You trained your model, and now you're seeing how good your model is. How good your model is using your test set that the model has not seen before. And when we do this, then the model, the MAE for this is 0.254. But because this was an exponential model or exponential price, we had to, the log price, the log price. So we have to convert it back to the actual dollar amount by taking the exponent. I hope that this makes sense. So we calculated the MAE, which gives you this number. But in real dollars, this is your error. So for every house that you're predicting in the testing set, there's on average error of $30,000. I hope that makes sense here. I know, it's like nothing, right? I mean, depends on your definition of too high. Okay, another evaluation metric that is commonly used is the RMSE. So the root mean square error. So remember again that when you take the difference from the prediction from the actual value, you have to fix these plus minuses. And instead of taking the absolute value, here you're squaring it. Right? So you add it up. And then you bring it back by taking the square root. Prepare it to calculate correlation between the prediction and test values. Like Diego, I'm assuming to evaluate your model. I'm not sure if I'm following, but that's not how you evaluate your model necessarily. I mean, all of them are in the value that you fed your data in. So when we calculate this, you still have to bring it back, the sell price, to actual dollar amount, right? So these are like different metrics of calculating your errors. So the true sell price is 0.36, well, but it's the exponent that you need to take. So it's this much in dollar amount. This is 43, right? So it went up a little bit, but this is just a different metric on how minus 1 full bedroom between model and actual data. Not sure if I understand what you're saying, but okay, let's clear this. Okay, so, and the last one that I'm going to introduce here is the mean absolute percentage error. So this one is a little bit different than the rest of them. Let's see. Oh, there you go. In that you're not, I mean, you are still calculating the difference, but oops. So from your prediction to the actual, but then you're dividing it by the actual and taking the absolute value. And this is what you're summing. And then of course you have to divide it by the number of samples, and you essentially time it by 100 to get a percentage number. Okay. So let's clear this. Do these options fairly original? Yes, Lisette. So we're evaluating the errors for everything, and this is what we get. So for the mean absolute percentage error, so on the average, we are off by 30%. So, I mean, you could kind of say like we're right 70% of the time. That's a different way of putting it, right? Or it's not quite that. It's like we're most of the time, it's an okay model, right? It's not perfect, but it's doing a decent job. All right, how are we doing? We are okay on time stuff. So this is kind of looking into some of this difference in like why we use which one, right? Why don't we just use one? Like they're all the same, you will think. It's not quite true. Often they will behave well in perfect scenarios where your data is clean, you don't have any outliers. All these metrics should behave similarly and will give you the same conclusion. But you know that your data is not always perfect. Pretty much never is. So there's differences in how mean square error, it puts more weight on the outliers because they're being squared before you average them, right? So when you square them, you're multiplying that effect. I hope this makes sense. I give you 1 minute to like read through this in hopes that it makes sense to you. Yep, 30% MAP is, yeah, 70% of the time is doing well or accurate. Gives you the accurate prediction. Why the MAP? Oscar, I'm not sure where you're pointing this here. I think it might be a different model. Oh, you're saying like between the numbers that I get and your numbers. Maybe. If that's the case, there might be just like a slight difference in like how your data was split. Perhaps. I'm not sure. Okay, I hope this makes sense. And if it doesn't, let me know. I try to address it. Also, read it over. I know you have great others, your families, great TAs that are ready to help you out. So use them to your advantage, okay? Okay, so these are the formulas that I was just drawing with my squiggles. But you have them here, and so it's actually a better readable form. All right. So let's move on to the next exercise. And compute to your log model and see how the values compare. So take a moment to do this. Let's give it a few minutes.
Won't you take me to that place when I lose my sense of time, where I escape my fate, when my won't you play my favorite? I don't wanna wait. I don't wanna wait. Yeah, so yeah, Zane. I wanna feel it in my body. I feel it in my body. Yeah. Feel it in my veins. Wallah, I feel it in my body. I feel it in my body. Yeah, so yeah, Zane. And play my favorite song. My favorite song. Play my favorite song. Won't you play my favorite song? My favorite song. Play my favorite
Favorite
song.
song. What's the name?
Oh, when I see
Or just favorite
you,
song?
you wanted to come on. Oh, when you wanted to come on. You wanted to come on. Oh, when I see you wanted to come on. Oh, when you wanted to come on. You wanted to come, Oh, when I said you wanted to come on. Oh, when you wanted to come on. You wanted to come on. Won't you play my favorite song? My favorite song. Play my favorite song. Won't you play my favorite song? My favorite song. Play my favorite song. Won't you play my favorite song? My favorite song. Play my favorite song. Won't you play my favorite song? My favorite song. Play my favorite song. Won't you play my favorite song?
All right, how are we doing? It looks like some of you finish. So let's look at this. So we're fitting the linear model first, of course, and then we get the MAE and the RMSC and the MAPE. Okay, and if you remember correctly, the log model had pretty similar values, but so if we look at MAP, it's pretty similar, so 30%. The RMSE, it's $43,000, whereas this is also $43,000. And then here is 29. Where did they go? Oh, right, sorry. It's comparing it right here. I'll have to scroll back. So the linear model has $31,000 versus the log model has $29,000. So it's a little bit better. And same here. The RMSC is $44,000 in errors. And then the log model is $43,000 in error. So in all accounts, and also the MAPE also says the errors are 34% versus 30% for the log model, right? So in all metrics, you know that the log model is doing better than your linear model. Okay, so this is how you could compare, once you build a model, you compare these models and how they're performing. Why we calculate a model using training set? Yeah, so this is exactly what I was talking around, Dorian. So you don't want to assess your model with your train set because that's what you use to train your model. You want to test it with some data that the model has not seen ever. And that's really how you assess how well your model is doing. If you use it, if you assess doing the train set, you're gonna get really good numbers here. It's gonna be essentially perfect here because that's what the data you use for it to train, right? The model by default is going to be performing better in almost all cases with your trained data set. Not always, but like it's very common that that's the case. Versus when you assess it using your test set, but that's really the true measure of how well your model is doing, is when you're tested with some data that the model has never seen ever. And then the difference in sizes is because you want to use a lot of your data to train, but you also want to save enough to have a good evaluation. So that's why it's pretty common to do 70 to 80% for your train set and then 20-30% for your test set. It depends on the size of your data. Sometimes you could sacrifice more than others, but that's how we build models in general. I hope that helps. Okay, so we have should probably, let's see. We have until 11, or sorry, 12:20. Is that right? I'm confused. What time is it over there right now? Can somebody type that for me? 12:03. And we have until 12:15. Is that correct? Okay. Thank you. So I'm gonna kind of semi-skip this part. This is just a demonstration of how these different metrics will behave depending on your model and your data set. So in this case, you have a data set that the training set, that the whole data set only has one outlier. Okay? And that's how you end up with the metrics, where depending on which metric you're using, you may be flipping. So for example, in this case, it says, okay, model 1 is better, but RMSEE says that the model 2 is better, right? And then again, MAP says that the model 1 is better. If we remove that one outlier here, then we go back to seeing what we expect, the model 1, which is using the test set. Oh, sorry. So this is, where's the model 1? Yeah, so the model 1 should be looking more like this. And then this other random model that we used, okay? So you could see here that the RMSEE behaves a little bit different when you have outliers. When you remove them, that effect goes away. That's really more what this is doing. So in the interest of time, I will let you review this. I hope that it makes sense to you. If you're confused about this, feel free to reach out to your TAs, okay? Okay, we could also add features to improve our models. We could actually make features that don't exist here. And this is called feature engineering. I'm not sure how much you've talked about engineering, but you could like do this differently by like changing or multiplying things and of some sort, right? So in a lot of the linear regressions, you could keep adding and adding training sets, but again, the more you add, the higher likelihood that you're going to have a really, really complex model that is overfitted, and it may not be a good model to be generalized. Okay, so for this one, we're using a new model that actually adds quite a bit of features. And this is like the interesting part of how you could handle numerical values differently. So you could handle them as the year here, for example, as a numerical value or as a categorical value. Okay. Let's take a minute here for a second to see if you could think about how you could build this model. You've been building a lot of models. I hope this is becoming a little more, it's becoming to make more sense when you put them into code. Luis, that was just a random model that we knew it wasn't going to behave well in a normal situation. Okay. So, and by adding a C parenthesis in front of it, you could actually make those categorical variables. So first we are defining this function that will convert any feature to, well, not any, but it will extract the year from a date. Okay, so we'll convert it to date time and then extract the year. And then we are adding this, and let's see here. Yeah, so we're extracting the year from the cell's date and then convert it to categorical. And we fit this in using the train data set. Okay. And so let's see here. So we have this, and now, oh yeah, this is a good exercise. How would you interpret the exterior wall that is brick of 0.0236 here? What do you think? A property with brick external walls is predicted to have a log price that is 0.0236 higher than a property with aluminum vinyl external wall that is otherwise identical. B, increased by 0.0236, all S being equal. Or C, 0.0236 higher than the average property in the training set. Are you all taking a nap now? Is that what you're saying? Okay, so A, B, or C? Okay, we got 1B. B, we're getting a lot of B's and A's. A lot of B's. I'm curious to hear, why do you think, well, so let's find the exterior wall here. They're here. Starting here. Right. Block, brick, cement, frame, wood, stone, stucco. Remember that when you have categorical values, or sorry, variables, you're always going to be in reference to the base category, right? So in this case, it's going to be the aluminum vinyl external wall. So the answer is actually A. So in comparison to the houses that have aluminum or vinyl external walls, and everything else is the same. So everything else is the same except the aluminum vinyl external wall is going to be the base. Compared to that, having a brick wall is going to be 0.0236 higher. Like, is this a linear model? I think this is a, oh no, this is a log. So you have to convert this to take the exponent in order to get the actual dollar value. Okay, so A is correct. Oops. We're almost here, so let's I might go over a little tiny bit, but bear with me here. I try not to go over more than 5 minutes, okay?
It's okay, Emiko. Thank you very much.
Mm-hmm. All right, we are going to be computing the mean absolute error for this model that we just built to the original model that had less features. And how do you think when you compare that? So I'm just going to show you the numbers actually, because I want you to be able to interpret this. So can you write what your conclusions for this is? Is this performing, which one is performing better? So which model is performing better? Yeah, for those of you who said the model feed model, why, can you give me a why? Just like one reason why you said that. Lower AIC. Yeah, that's a great metric to start with. Also, as you can see, for all metrics that we are looking at, everything is better in this new model where we added more features. All right. I think somebody else, like, this is also taking the the log of the sell price. So these are all like log, but except for the MAE, we already converted this. But the R square, it's 0.8 versus for the log with less features, it was 0.6. So you could see here that adding more feature helps in the performance, right? Yeah, so all the metrics are pointing to the feature being better. What if the Andres, I'm trying to think of a scenario, but like whether that will be the case. Let me come back to you on that. So I can't think of right now like a scenario where that would be the case. Yeah, I mean, like an overfitting model will behave very strangely sometimes. So especially the MAE will be a little bit off, I would say. The AIC is probably one metric that it's good to figure out whether you're adding the features that you're adding are making a difference to your model. I think that's really like a really good way to figuring that out. Okay, so what story does this model tell us about Milwaukee housing market during the last 15 years? And so I'm gonna give you the answer here. So this is D. The prices had increased until 2007 when there was a housing crash. And since then, the prices have slowly risen, but they have not yet fully recovered. And we can make these conclusions when we plot these coefficients. Okay? So if we plot the coefficients here, you could see here that it like really went up and then it crashed. And it has gone up a little bit plateaued and then like it started to increase. I bet right now it's like skyrocket high around here, but we don't have that data right now, of course. Because the housing market in the US is extremely crazy
Record
right
to the
now.
cloud.
Recording in progress.
Diccionario.
Not sure. Shouldn't really be taking any longer than the other ones, but well, it
Acabó
might be because you're
cálculo de la
looking for
matriz de
features.
transición. Aspectos para el cálculo del factor de
I
ajuste.
guess you're right. Like it will take a little longer time, but I'm not sure by how much. Okay, so I
Una
hope
página
this
web ahí
makes
embebida.
sense
¿Listo?
here that the coefficients explains the trend in this market here.
Welcome again.
That happened on that first index or the rows, and we can see it based off
Okay,
of
so
this is
here
status.
we
You know,
have
is that location
a townhouse, a two-story, so 2 levels. So first floor, second floor. Townhouse that it's selling for $150,000 with these
hay algo que
features. Okay, and then we could use our model to say, is this a good price? But when we actually ask our model, tell me, given these features, what would our price be? And it says it's more like $130,000, right? So we will kind of say like, okay, maybe, well, this is like way too overpriced, but then there's a difference in years, right? Which our data doesn't really go beyond 2018. So that might be some explanation. Yeah, so let me just quickly go over, because this is like the last thing, collinearity and standard errors. So when you add features, I'm just gonna say this, when you add features, you're more likely to start creating collinearity issues. So that means collinearity where 2 features are actually dealing with the same or similar thing. So we could, this set of questions here, I will go over this. And what I could do is also, I will keep explaining, and if you want to take a break until however long, feel free to do so. Otherwise, I will let this record and stop the recording, and so you could watch it later, okay? Does it sound like a compromise here? And Yeah, Andres, feel free to go. Like, I know it's your time. So, and this is recorded again, so it should be okay. Okay, so again, the more features you're introduced, the more likely that you're going to be overfitting things. So you could be destabilizing your model by having too many features. And this is very true when we introduce this extra feature
Record to the cloud.
where we are taking the log of the ratio between the lot size and the square feet of the house. But we're adding just a tiny bit here, so it's not a perfect match. And that's just so that we don't generate zeros divided by zeros. Okay. And when we do that, so let's see here. Let's take a look at the coefficients here for these two. 0.5337, 0.1156. And then when we look at this other one where we added this extra feature here, the introduced features that we know it's going to cause a problem, look what happened here. These two are like completely different now. And then there's like this also extra feature that are like very large negative or very large positive number. Again, feel free to go on your break. Right now, this is completely unofficial right now. I'm just making sure that you have the explanations a little bit for you to look at it later. So you could see here, but just interested in this one feature that it's completely collinear, which means when you compare it here, this correlation, you have this high collinearity of with the square feet and the lot size, right? So they're both positive 0.7 and negative 0.7. And as you can see here, it actually, there's a lot of other features that we didn't generate on purpose, but they have a high correlation. And these will be causing collinearity issues. Okay, so it's always like good idea to look at like these collinearities when you're doing linear models. Okay, so again, you're going to be learning a little bit better ways to, not better, but like different ways to handle these collinearity and how to handle them. But I hope that this is a good introduction for like engineering features, like you know how you could engineer, and also you know how to look out for collinearity in your model and stabilizing your linear model. Okay, so I hope this was helpful. Let me know if you have any questions, and I'll stay for another minute. But if you have questions that you're very not clear, feel free to like go over again, read it over on your own time or rewatch the video. And also, again, you have great TAs. I know you do. So
thank you very, very much, Emiko. And as you know, guys, you can also review and replay the videos and the recordings on the training site. We hope you have liked this case and you have learned a lot. And thank you again, Emiko. It was like really, really nice of you. I know we got a little bit, over the time, and we do appreciate that because Emiko wanted you guys to be like, fully sure about what you were learning. So let's go for and grab lunch, right?
Yeah. All right. Thank you all. Bye.
Bye, Emiko. Thank you very much. Bye, guys. Remember that you have your team meetings awaiting after lunch. Take care.